aldehydes and ketones. So we have a few pictures here on this first slide. I just thought these were cool ways to remind you of how aldehydes and ketones play into our health and molecules that we either come into contact with or that matter physiologically. So anybody citronella candles? I'm a huge fan of those in the summer. We have a lot of mosquitoes and stuff sometimes, especially after a big rain in Arkansas. So I thought it was interesting that the very molecule for citronella has CHO. This is an aldehyde group. This is the way we abbreviate aldehydes. And then I was reading a little bit, and this huge drug-looking molecule right here, it is one of the newest classes of chemotherapy agents. And the parts that I have circled in here, anybody recognize what those are that I have circled in this? I don't know, paclitaxel, probably really botched that. I don't know how this is pronounced, but those are ketones, okay? So there's a lot of different ketones and other functional groups in this molecule. So that was a really cool find. And then, you know what, glucose. We're gonna be talking a whole lot about glucose in like next week, I think, or the week after. Yeah, next week we get to chapter 20. So glucose has right here, what functional group is this? You guys gotta talk to me.
Is that an aldehyde?
It is an aldehyde, okay? It's an aldehyde. So glucose, a lot of different sugars, monosaccharides. When we get out to all that, you'll see aldehydes a whole lot. So what we're talking about today, not that the other stuff isn't building the foundation, it all is, but you're gonna see a whole lot of aldehydes and ketones moving forward. So the carbonyl group. So the base part of the aldehyde ketone functional group is what we call the carbonyl group, and that is this right here. It's the carbon bonded to double bonded to an oxygen. And I want to point this out because this separation of charge that happens, because this is a polar bond. So this is a polar bond. And the separation, because it's polar bond, we say that the oxygen is it's more electronegative than the carbon. So we put the partial negative on the oxygen. I put the partial positive on the carbon. And that's, if you remember that, it's going to help you with some of the reactions we're going to talk about today. It's going to help you remember how things are going to go where. Because remember, negative is attracted to positive and positive is attracted to negative. So if we know how the separation of charge works on a carbonyl group, it's going to help us. All right, so that is the base portion, double bonded to an oxygen atom of carbon. And then we classify carbonyl compounds because there's a lot of functional groups that have a carbonyl in them. Okay, aldehydes and ketones being two. But we classify carbonyl compounds by what, I'm gonna highlight this, by what is bonded to the carbonyl carbon. So this is where we can tailor and customize and get all these other different functional groups, be it esters or amides or ketones or whatever, based on what is bonded to that carbonyl carbon. Okay, so there's two major groups of carbonyl compounds, and aldehydes and ketones are on one side. So if we're looking at these, why are we classifying aldehydes and ketones together? I want to read this. The carbonyl carbon here is bonded to either carbons and hydrogens. All right, so if you're looking at these carbonyl carbons right here, these little R's and H's are just either carbons or hydrogens. So an aldehyde, that carbonyl carbon is bonded to a carbon on one side, a hydrogen on the other. On a ketone, the carbonyl carbon is bonded to carbons on either side. Now we know carbons and hydrogens are not electronegative atoms. They don't really strongly attract electrons, okay? And that's what I'm saying right here, is that these are atoms that do not attract electrons, and that's gonna affect how the functional group behaves. On the other side, the other style, or the other way we classify things, we got carboxylic acids, esters, and amides. Carboxylic acids, esters, and amides. Now here, the carbonyl carbon, the carbonyl group, is bonded to carbons, oxygens, nitrogens, okay? And especially, so look, right here, this is what I'm talking about, oxygen, oxygen, nitrogen. Now they're all bonded to carbon on this side, but on the other side is where you get things that are unique and are different for that particular group. Oxygens and nitrogens are very electronegative. Okay, and that's what I'm saying up here. these atoms do attract electrons, those oxygen and nitrogen. And that's going to play into effect, that's going to have an effect on how these functional groups behave and what kind of reactions they perform, okay? All right, so just be aware of that. That's how we classify these. That's how they're different. Let's look specifically for a little while at just aldehydes and ketones, okay? So aldehydes, couple things. It's not so important right here, by the way, that you know the bond angle, but I put this figure on here just so you can see. It is a planar triangular type of geometry. Okay, but aldehydes, again, this is what they look like. If you're writing it in a condensed form, you would have the R and then CHO. CHO. Okay, so this is how we abbreviate the functional group as CHO. Now, I wanted to point out this is very similar to alcohols. And I want you to know how it's different. An alcohol, we abbreviate it as a carbon bonded to an OH group. Okay, so you see how they're very similar? So just remember, aldehyde is CHO, but an alcohol is a carbon bonded to an OH group, COH. Okay, now in a line structure, you have to draw the H in. What that means is, so if I draw my aldehyde like this, and I say a carbon, and I just draw two lines like that, I've actually not drawn an aldehyde. Well, that's not a complete line structure. In a line structure, you don't draw the carbon in, right? So it would actually be like that, sorry. So that's not an aldehyde. So you have to explicitly show the H if you're drawing an aldehyde. And you're including, like if you draw, if I something on an exam and you choose to draw the line structure, I love line structure, so I encourage you to draw line structures, but if you want me to know it's an aldehyde, include that H right there, okay? And the other thing is that these carbonyl carbons in an aldehyde, they're only bonded to one other carbon, they're a primary carbon. So what I'm saying is this right here, this is a primary carbon. So aldehydes, they're always what we say terminal. They're always terminal. They're the dead end of the structure. They're always on the outside perimeter. And that's what you noticed even with glucose. That aldehyde group on glucose, it's right here at the top, okay? It's terminal, it's not internal. And that's different from a ketone, okay? Ketones are internal. Am I going too fast? Are y'all good? I can zoom back out if y'all need to see everything. Ketones are internal, okay? This is the carbonyl carbon, and it is bonded to a carbon on the right-hand side, or sorry, left hand, and a carbon on the right-hand side. And so the way and those are not necessarily identical groups. So that's why we put this little prime sign right here. We say R and R prime, just indicating we have two different carbon groups. They don't have to be the same, they can be different. You could have a methyl on one side, an ethyl group on another. I mean, the possibilities are endless. It could be in a ring structure. So the way we abbreviate it as a condensed form is R, C, O, R prime, indicating those two different carbon groups. Or you could draw it like this. We got R2 indicating, okay, the two R's, and then we got the carbon double bond, the oxygen. All right, now the functional group abbreviation is COR prime, and we got this line right here indicating it goes to the other R group. But opposite to aldehydes, because this carbon is bonded to two other carbons, the carbonyl carbon, we say this group is always internal. So if you're looking at this molecule down here, we got acetone right here. The ketone, the functional group, is in between two other carbon groups. It's not on the end of the molecule. It's in. That's why we say it's internal. Okay, and then there's just the line structure for a ketone. Okay, there'd be the carbonyl carbon. That would be one R group, some other carbon group, alkyl group, and then another alkyl group here. So I want you to take a minute. We're going to do just a couple of these. I'll leave a few of you to work out on your own for more practice. So let's just do the first two, prostaglandin and testosterone. These are what these molecules look like. And I want you to circle anything that is an aldehyde or a ketone. So don't worry about other functional groups, but anything that is explicitly aldehyde or ketone, circle that. So on prostaglandin, how many things are you guys circling?
I just saw a ketone on the first one.
Yeah, it's right here. Okay, there's the ketone. So there's the carbonyl carbon, and it's bonded to a carbon group there and a carbon group there. So that is the ketone. Okay. Now, if you're wondering, do I need to circle all the carbons? You can just circle the carbonyl carbon and the oxygen for me, as long as it's the right one, and I'll understand, okay, that's the ketone. And that should be it. This is actually a carboxylic acid. These are alcohols down here, so none of those are aldehydes and ketones. All this is CHs, so none of that is, and we got an alkene in there, but no other aldehydes or ketones. Okay, what about testosterone?
There's another ketone in there.
There is a ketone, Abby, right here. And I think that's it. I see an alcohol, I see an alkene, I see those methyl groups, but that's it. Okay, what about, we'll keep going because there's fewer functional groups than I remembered or thought. Vanillin, flavoring agent. Pure vanilla extract is really, really expensive. I always do imitation vanilla. We went to Mexico on a mission trip a few years ago. And my grandma always told me, you can buy like huge bottles of vanilla down there for really cheap. And I was like, they stopped doing that deal because I couldn't find any. I was so mad. Okay, vanilla. Anybody see an aldehyde or a ketone on here? You're looking for, remember, CHO or something like this, since a lot of these are line structures.
There's an aldehyde.
Yeah, that's what I was gonna
Cameron
say.
got it. Yeah, right here. There's the aldehyde. What is, I know we're not talking about this, but what is this right here? Or I guess I could say, what is this right here? Anybody recognize that? So there's a carbon bonded to an oxygen. And then I would prefer to write this methyl group like this. So you could see that oxygen bonded to this carbon right here. What is that? Did we talk about him yesterday? I forget what day we talked about him. This is an ether. Okay. It was actually one of your chapter 12 homework problems you got groups that look like this. Anyways, okay.
Question. Aldehydes, do they not always have double bonds?
They do.
Can you explain? Oh, sorry. Can you explain to me how the vanilla has the double?
Yeah.
Oh, that's aldehyde.
That's a great question. So we got, if I got my ring structure right here, if we actually just draw this out, well, they have the double bond there, there, and there. Okay, so right here, we have this carbon. Now think, carbon's gotta have 4 bonds, okay? So this, it looks deceiving when they write it like this. This is not what we have. Why is this not what we have? Hydrogen can't have 2 bonds. Carbon's gotta have more than 2 bonds. So don't think of it like that in your head. Just because you see the abbreviation CHO doesn't mean that's how they're exactly bonded together. We have the only possible arrangement is this right here for everybody to be satisfied. That is the only way. You could try it 6 other ways or however many you could think of, and you're not going to get all the atoms satisfied. That's the only arrangement. So that is why that is an aldehyde.
Thank you.
Mm-hmm. Okay, what about this right here? C4H9. I'm not going to worry about drawing out all the hydrogens, but I got 4 carbons. 1, 2, 3, 4. And then I got this, so that's these 4 carbons. And then I got it bonded to another carbon right here. So that's this carbon. Okay, so that's this carbon 5 and that's carbon 5. And we got this O and then a CH3. So I got a CH3 right there. So that's carbon 6 and that's carbon 6. What about this O? How do I do that into my structure? Some of you might have thought, oh, I thought it was going to look like this. O and then CH3. But if that's the case, this carbon is left highly unhappy because it only has 2 bonds. Because look, there's no hydrogens indicated that's bonded to this carbon. So this cannot be the right structure. So I gotta erase that. So how should this look? I'm gonna rebond that to my ending methyl group right there.
Would you double bond the carbon to the oxygen?
So what does that make this?
Is it a ketone?
It is, because we got a carbon there and a carbon there. We could say this is R and R prime. Whoops, prime. Does that make sense? That's what we were looking at right up here. Okay, so yeah, that's the ketone. Okay. What about this one? I'm not even gonna draw this out. CHO is what?
Aldehyde?
Yeah, that's an aldehyde. Okay, that looks like this. And then this C4H9 part is the rest of that. Okay, does that help in identifying a little bit? Recognizing them? Either in condensed structures or line structures? Okay, naming. Aldehyde's pretty simple. You just put the word aldehyde on the end, all right? And you smush it into one word, okay? So this would, for example, acid aldehyde, all right? Benzaldehyde, all right? Now for IUPAC naming, that's the common name, sorry. Simple aldehydes have common names that end in aldehyde. For IUPAC naming, you take the E off from the parent alkane and you replace it with Al, all, okay? So if we have this, look at this very last one right here. 3-methyl-butanol. And the numbering, oh, we should probably read this last sentence regarding how we're supposed to number it. When substituents are present, the carbon chain is numbered beginning with 1 for the carbonyl carbon. So that's why they numbered this right towards left, starting right to left. They recognize, okay, this right here is my carbonyl group. It is an aldehyde because I have this H right here. So the name ending is Al. In my longest chain, if I'm counting my longest chain, I've got 1, 2, 3, 4 carbons. So it's a butane, but because we got the aldehyde, it's butanol, okay? And we got this Al right here. Now we also have this methyl substituent branched off carbon 3. So that's why they say 3-methyl, and y'all are familiar with how to do the substituents by now. Butanol. But this, it's what's important and what's new here is that my carbonyl carbon is numbered 1. Okay. And they don't have, it doesn't tell you to put the 1 in. It's not 3-methyl-1-butanol. It's understood here that that carbonyl carbon is 1. So you don't have to include the 1 when you write the name. Okay, how do we name ketones? Simple ketones have common names. And the way you name those is the 2 alkyl groups bonded to the carbonyl carbon. You just name both sides, very much like an ether, but then you put the word ketone at the end. So the best example that I have here is this one right here. When they named it methyl ethyl ketone. That's the common name. But then there's the systematic name that's just underneath, okay? The systematic name you see in the parentheses right underneath is 2-butanone. What the heck? How do we get that? Well, let's read the next sentence. To get the systematic IUPAC naming, take the E off from the parent alkane and replace it with, instead of saying 1, it's, you pronounce it "on." Okay, that's why, like, say the word ketone. Okay, you spell it O-N-E, but it's not key one or keep one. It's ketone, so you pronounce it "on." And the numbering this time is of the alkane chain begins at the end nearest the carbonyl group. So that carbonyl carbon isn't always number 1 because ketones are internal. Aldehydes, they're terminal. So we can't always number the carbon as number 1. But ketones are internal, so we're just gonna start at the end closest to the ketone functional group and give it the lowest index. That carbonyl carbon will get the lowest index number possible. So that's why when we're numbering 2-butanone here, we got 1, 2, 3, 4 carbons right here, 1, 2, 3, 4. So as an alkane, it would be butane, but we just take the E off, put O-N-E there, so butanone. And we do put the number here too, to indicate where that carbonyl group occurs in my line of carbons, where that ketone functional group sits, what carbon it's bonded to 2-butanone. Next one over, we've got 1, 2, 3, 4, 5 carbons. All right, so you could, the common name, this side is a methyl group, this side is a propyl group. You could say methyl propyl ketone. The systematic naming though is you name the longest chain. There's 5 carbons in the chain, so instead of pentane, we say pentanone. And then we put a 2 there on front to indicate where that my carbonyl group sits right on carbon 2. Okay, 2-pentanone. We had 2-butanone, 2-pentanone. All right. We have a ring structure. So we've got a 6-member ring structure. 1, 2, 3, 4, 5, 6. So that's cyclohexane. It doesn't matter. All carbons are considered identical here. Okay, all carbons are considered identical. So we don't even need to number, especially if there's no other groups, like there's no other substituents branched off my ring, no methyl groups, no ethyl groups. If it's just the ketone, you just cyclohexanone, the O-N-E ending. So instead of cyclohexane, cyclohexanone. Now, the moment you throw a substituent on here, it's a different ballgame. You got to name that. You always number this carbon as number 1. Okay.
Hey,
So
Dr.
we have.
Oh, sorry, go ahead.
Oh, go ahead, Abby. What was your question?
Well, I was gonna ask on these, do we have to keep them in alphabetical order like the other ones?
Because they didn't on methyl ethyl ketone, did they?
That's what confused me. I was curious.
So, yeah, that does look confusing. I would, since you guys are so used to practicing putting things in alphabetical order, that's what I would do. I'm not going to count you wrong if you told me that was ethyl methyl ketone. I would absolutely accept that. Okay.
Thank you. Sorry.
Maybe there wasn't a rule anywhere. There's not a rule anywhere saying that you have to name the left side and the right side, but that looks like what they're doing. But if you ever have a question, just put it in alphabetical order. I would certainly accept that. Because whether you invert this molecule 180 degrees or not, it's the same molecule. Okay. All right, great question. Any other questions? Okay, let's put this into practice. I want you to try to give the systematic name, not the common name. So we're not doing the methyl ethyl ketone thing here. We're actually doing the systematic name. So this is definitely a ketone because that carbonyl carbon is internal, not terminal. So take a second. You need to count the carbons in the longest chain. So if we do that, and you got to start at the end nearest the carbonyl carbon, right? So you can't start numbering from the right side. You have to start numbering from the left side. 1, 2, 3, 4, 5, 6. So hexane is our parent name here, but we know we have a ketone. It's a ketone. So it's, all you do is take the E off. So literally spell out the whole word, but just remove the E and then add O-N-E. And then what do I need to put out front?
A 3.
A 3. 3-hexanone. Okay. We'll do a little more practice here. And notice I have it both ways. I say, draw the structure, and then here's the structure, give me the name. So I would encourage you to do all of these before the exam, just for extra practice. But I'll do 2 on the left side, and we'll do 2 on the right side, and then we'll move on. So octanol. Octanol. What do you guys think this looks like? Think about like octane. But instead of octane, it's going to be octanol. Remember, Al ending indicates we have what kind of functional group here? Yeah, Madison said it, but you're muted. An aldehyde. So you can draw Lewis structure, condensed structure, or line structure. I'm going to do a line structure because for me, those are the quickest. So I've got 8 carbons here, and it does not matter if you branch the aldehyde group off the right or the left side, the very first or last carbon, because either way we could flip the molecule over 180 degrees and you get the same thing. So what I'm saying is you can branch it off of this and call this carbon 1, and then remember you always have to show the H. Or you could branch it off of this one and show the H and say, okay, that's carbon 1. Either way is acceptable. We don't have any other functional groups here.
Would we be able to like do a line structure and then just tack on CHO? Or do you want us to do the double bond? and show
So
the
you're
H?
saying, could I do this?
Mhm.
That's fine, Claire.
Okay.
All right, I like D as well. Let's look at D. This is a common naming. And this is a ketone. Methyl tert-butyl ketone. Now, oh, by the way, I did want to ask you, does anybody remember what a phenyl group is? Because if you try to draw that one out later on your own, what is a phenyl group? So when we talked about aromatics, real quick, we talked about, talked about benzene. We said when benzene itself is a substituent, so it's like a group branched off of another molecule with another functional group, that is called a phenyl group, okay? So remember that is phenyl. So when you try to draw B. All right, anybody got D, methyl tert-butyl ketone? Well, I know I've got a ketone and it's in the middle. On one side, I have a methyl group. On the other side, I have a tert-butyl group. What is tert-butyl? Here's my methyl group. Tert-butyl is a group that is got 4 carbons because butyl indicates 4 carbons. And it looks like this, and you're branched through the middle carbon. So it is attached to the rest of the molecule through this middle carbon. So you got CH3 groups all around it. Okay, and you could also draw the line structure, would look like this.
What does a tert mean again?
Tert means that you're attached to the tertiary carbon. So this carbon right here in the middle is a tertiary. I'll put a 3 with a degree sign. That's the tertiary carbon. Why? Because it's bonded to 1, 2, 3 other carbons. Remember how we classify carbons as primary, secondary, tertiary, quaternary? So because we're branching this whole group through that tertiary carbon, that's why it's called tert-butyl.
Okay, on the H3C that's on the left.
This
Does
right
it have
here,
to be HC3? Like, could you write CH? Yeah. Could you write CH3? Like, does it matter?
Maggie, that's a great question. You'll see it written both ways. You could write it like this, okay? But I want you to know that's this carbon right here is bonded to the carbon and not the hydrogens. So you'll tend to see me write it C and then the H3 on the other side of it. They're both ways to write methyl groups. that is specifically, you see this specifically when you're trying to branch the methyl group off the end on the left side of a structure, is when you typically see that. When you're writing, extending things out to the right, you can write them in normal fashion. But great question, Maggie. Okay, let's do 2 over here and then we got to move on. Let's do C and let's do B. Okay, y'all write the names. Okay, B is a ketone. So if you do, you can either do the common or the systematic. I'll write both. That's the common. Notice that the ketone is right in the middle. So it doesn't matter on B if you start numbering from the right or the left. That's the systematic name, 3-pentanone. So instead of pentane, it's pentanone. Okay, C
Sorry,
is
wait.
C.
What? Why is it diethyl?
Oh, diethyl. Anybody want to answer that for me? Anybody feel confident on why that's diethyl?
Is it because you could technically have like the branch for the CH2, CH3?
Yeah, so Cameron, the common naming looks at the left side and says, okay, what's branched off on the left side? That is an ethyl group. And then it looks at the right side and says, okay, what's branched off on the right side? Guess what? Another ethyl group. So whenever you have 2 identical groups branched off of something, you use the prefix di to indicate that there's 2 there. So that's what I put. That's why I put diethyl ketone.
Oh, I thought that was considered as a main chain.
It is. So for the systematic naming, that's why we named it 3-pentanone. Because in the main chain, so there's 2 styles of naming, and the rules for that are right here. Common names, whoops. The common names name the 2 alkyl groups bonded to the carbonyl carbon, and then they add the word ketone. Okay, so when I say carbonyl carbon, that's this one right here. They look at, okay, what's bonded to the right, we'll name this group. What's bonded to the left, we'll name that group, and then we'll throw on the word ketone. The systematic naming, it names the parent alkane, and it changes the name ending to O-N-E. And that's why down here, I counted all my carbons. I said, okay, I got 5, that's a pentane, but it's pentanone since there's a ketone functional group in there. And I put the 3 to indicate off what carbon is that ketone, is it on the molecule? Does that help, Cameron?
Yes, thank you.
Okay. The way, just so you know, the way I'm bent, if I'm going to ask you a question on the exam, I'm going to tell you to give me the systematic naming. Okay. But I want you to know both because they're honestly, especially when you get to biochemistry, used so interchangeably. You guys probably aren't going to go any further in organic chemistry, or else you would see this a whole lot. But in biochemistry, you'll see the common naming too. So that's why I'm telling you both. 3, we got to do 3 really quick. So what is 3? Is it a ketone or an aldehyde?
It's an aldehyde.
It is an aldehyde, Abby. So we're going to change the name ending to Al. We have to start numbering right here. We call that carbon 1, 2, 3, 4, 5, 6. So this is like a hexane if we had an alkane, but we're going to change the name ending to Al. So hexanol. Let's skip that over. We don't have to put a 1 or anything out front like we do for ketones because we know carbon 1 is the carbonyl carbon for aldehydes since it's terminal. But we got this methyl group off carbon 4, so this is 4 methyl. I think we don't need a dash there, sorry. Hexanol. All right. Questions? So Cameron, I think a good one to practice is dipropyl ketone. You know what diethyl ketone looks like. I bet you could draw dipropyl now. But we're gonna move on. Any questions on naming? All right, properties. Okay, they're moderately polar because again, you have this electronegative oxygen on your carbonyl carbon, but it also depends on just the size of things. Okay, you can have these huge hydrocarbon chains bonded off your carbonyl carbon, and the bigger the hydrocarbon portion is, the more alkane-like it is, and the more non-polar it is. Okay, but if you have relatively small aldehydes and small ketones, those are pretty polar compounds. All right, so moderate polar, thus they have moderate boiling points and melting points. They have boiling points that are higher than alkanes because they're not pure hydrocarbons. You have an electronegative oxygen atom double bonded in there. Specifically alkanes of similar size, but they have lower boiling points than alcohols of similar size. So for example, look what we have. We have an alkane, butane. We have an aldehyde. We have a ketone. And we have an alcohol. And look at their, well, I don't have their molecular weights, but they all have very, very similar molecular weights. If you counted up the carbons and hydrogen and oxygen, we got the same numbers of everything, I think, or very similar, very close. The alkane has the lowest boiling point because it is entirely non-polar. All right, so it has, it's like a gas at room temperature. These are liquids at room temperature, and they boil around 50 degrees, so it's quite a bit higher because they're polar, but they cannot hydrogen bond with one another. Why? Well, they have lone pairs here on the oxygen, so they have acceptors, but they don't have a positively polarized hydrogen. They don't have any donors. So they only have part of the requirements of what it takes to hydrogen bond. So they're polar, but they can't, so they're held together by dipole interactions. And dipole interactions are stronger than what holds a butane molecule together. If you have a bunch of butane in a beaker and they're floating around, what kind of interactions are at play?
Is that the London dispersion?
Yes, that's why it has such a low boiling point, because those are very, very weak intermolecular interactions. These are polar molecules, but so they have dipole interactions, but they can't hydrogen bond. Look at the alcohol. The alcohol has the acceptor and it has a positively polarized hydrogen and it has a donor, so that we know alcohols can hydrogen bond. That's why it has, look, its boiling point is almost twice that of our aldehyde here and our ketone. So that's why it has such a high boiling point. It's polar and it can hydrogen bond, all right? So if I were to give you a problem like this on the exam, where I give you like an alkane or an alkene, or an entirely non-polar molecule, then I give you an aldehyde, a ketone, an alcohol, I say put them in order according to their boiling points. This figure right here helps indicate alcohols are always going to have the highest, the alkanes or the alkenes are always going to have the lowest boiling points, and then the aldehydes and the ketones will be in the middle. Okay, they have moderate boiling points.
So aldehydes and ketones can never H bond.
They cannot hydrogen bond, not with themselves. They could hydrogen bond with a water molecule, but if you have pure, for example, if you have pure propanol or pure acetone, it cannot hydrogen bond.
You said what will always have the lowest?
The alkanes or the alkenes, any molecule that's entirely non-polar. Okay. I'm not really going to get into these. I'm going to skip over those actually. So I just want you to focus on this last point down here. Simple aldehydes and ketones are water soluble because that carbonyl carbon, you don't have a whole lot of hydrocarbon portion to your molecule. you just have these little small groups. Okay, so they're pretty polar and they are water soluble. But the longer you make those hydrocarbon chains off of the functional group, the more non-polar they are and the less, just like with alcohols. The higher your carbon to oxygen ratio, the less soluble they are in polar solvents. Okay. So real quick, let's just go through. I wish I had made this into a poll question. I just didn't have time last time. Indicate, are these molecules polar or non-polar? And if you are still like, I just don't remember a whole lot about bond and molecular polarity, go to chapter 4. I think I put it in the very first slide on our first lecture, chapter 12. Towards the back of chapter 4 is a review on polarity. I'm more than happy to walk you through that if you want to meet up with me. Okay, what you should have is polar, polar, non-polar, and polar. Okay, because we got these oxygens in here, and C is the only one that does not have an electronegative atom. Okay, any questions on how that would affect boiling points and the trends there? Common aldehyde and ketones. Okay, so a lot of aldehydes and ketones are used as aromatic and flavoring agents. Okay, look, when I say I love this stuff, it's an understatement. It's like my favorite lotion. Okay, anybody aromatherapy, Bath and Body Works? They are used, if you zoom in on this, it says eucalyptus leaf oil. That is what is used in stress relief is my favorite. But you can see a bunch of other things. We already talked about citronella, cinnamon, okay. I don't even know, camphor, moth repellent, civitone, okay, certain perfumes. So you can see these have these aldehydes or ketone functional groups. So these are used as a lot as flavoring or certain aromatic in different soaps, cosmetics, perfumes. All right. I think y'all can do this. We'll do the very first one in case you're like, I'm not sure how to do it. The very first one. Identify the functional groups here. What functional group do we have in this very first one? Do we have an aldehyde or well, it just says the functional group. So we actually have more than one kind of functional group. What all do y'all see?
Isn't the top CH2OH, isn't it an aldehyde?
So we need to look at our carbon and draw this out. So I'm going to draw, this is the CO right there. So I go up to this carbon. I've got 2 hydrogens here, and then I have an OH group off like that. So is that an aldehyde?
No.
No, but what is it?
Alcohol.
Yes, it's an alcohol. So what else do we have?
Do we have a ketone bonded to the carbon in a double bond with oxygen?
Yep, that's a ketone. Because we got that carbon bond and that carbon bond. What else do we have? Nothing else new, but more of the same. Right here and right here, what are these?
Alcohol.
Alcohol.
Okay. What about on this next one? I see 3 functional groups.
Aldehyde.
Yeah, right here is our aldehyde. And then same as the previous one, we got 2 alcohols. All right, I think y'all could do the rest. Table 15.2. This is several common ketones or aldehydes, and I just want to point this out because, again, don't spend time memorizing these, but you are going to see a whole lot of this right here, this group right here. So there is a particular enzyme that we are going to talk about probably for the whole last half of the course, acetyl-CoA. So I want you to know when we say acetyl, this right here is an acetyl group, right? Now it just happens to be acetaldehyde here because of this hydrogen, but I want you to just familiarize yourself with this term, this word, and this particular molecule, because we are going to see this on a coenzyme that's really, really, really important biologically when we get to the biochemistry part. Okay, it's gonna be important. All right, but again, I think that's really the only thing I wanted to point out from this table. Okay, oxidation of aldehydes. So now we're getting into reactions. So far we've talked about identifying aldehydes and ketones, how they're similar and how they're different, and then naming them, and then certain properties associated with them, especially with their boiling points and how that compares to alkanes and alcohols. Okay, so that's what we've hit so far. Now we're going to talk about some reactions. This is going to be a little more complex, but you've actually already looked at some of this. We talked about oxidizing agents, oxidation reactions yesterday with alcohols, and this is kind of just a review of what we did yesterday. Remember yesterday we said, recall from this, alcohols can be oxidized to aldehydes mildly. If you do mild oxidation on a primary alcohol, you get an aldehyde. And upon further oxidation, so this was the mild part, and then we said you can get, if you do really strong oxidation, you go all the way to a carboxylic acid. So I've actually already told you what happens when you oxidize an aldehyde, because this was our intermediate yesterday. I want to show you the slide that I'm talking about. Right here. This was our intermediate yesterday. So we're just looking at this right now. When we oxidize an aldehyde, we get carboxylic acid. Okay, but I want to look specifically what happens. So it's not an intermediate today, it's just our starting material today. So we have an aldehyde and we have an oxidizing agent. This hydrogen right here is just converted to an OH group. So we have, how many carbon oxygen bonds do we have on our aldehyde starting out? How many carbon oxygen bonds, individual bonds, do we have on our aldehyde starting out? Just count the number of carbon oxygen bonds. Yeah, we just have two individual. It's a double bond, but that's two single bonds. Okay, 1, 2. Now, how many carbon oxygen bonds do we have on our carboxylic acid? How many
3.
carbon? We got 3. 1, 2, 3. Okay. So this is oxidation. Why? Because remember what we said about oxidation? I'm going to go back to our yesterday's lecture. Read again right here. Remind yourself. Oxidation in the realm of organic chemistry is increasing the number of carbon oxygen bonds. So for example, if you go from a carbon oxygen single bond to a carbon oxygen double bond, that's oxidation. Here we've gone from 2 carbon oxygen bonds to 3. So this is oxidation because we're increasing the number. Here we go. Of carbon oxygen bonds. So the H is converted on the carbonyl to an OH. So if I ask you, what product do you get when you oxidize an aldehyde? You get a carboxylic acid. Okay. So what about a ketone? A ketone is like, well, we kind of actually looked at this yesterday too, because when we oxidize a secondary alcohol, we get a ketone. But then if we try to oxidize that ketone any further, we don't get a reaction, no reaction. Okay, ketones do not have a hydrogen on the carbonyl carbon. All we have is other carbons. They don't have any hydrogen. And you have to be able to remove a hydrogen to add. You're not going to just break a carbon-carbon bond and throw an OH group on there. These are way more, carbons are way harder to pull off. Hydrogens are pretty easy to take on and off. Okay, but we don't have a hydrogen, so we're not going to oxidize it any further. Okay, so you get no reaction. All right, so aldehydes are oxidized to carboxylic acids. Ketones do not. Can y'all hear that noise in the other room? Okay, that's our liquid nitrogen tank. So sorry for that. They're filling it up right now. It makes the weirdest noises. They do not react with oxidizing agents. Okay, any questions on this? Okay, what if we do the reverse? What if we, instead of oxidizing it, we reduce it? So now we're just going to take away carbon oxygen bonds and we're going to make them back into carbon hydrogen bonds. So reduction of a carbonyl group results in an alcohol. All right. So I really like this figure. Okay. Because it just kind of summarizes everything we've talked about. If you have an aldehyde or a ketone and you're reducing it, you get an alcohol. But if you have an alcohol and you oxidize it, you either get an aldehyde or a ketone, depending on what these groups are right here. Okay. Now, I think I told you guys there's some stuff I decided I'm going to skip over for time's sake, and this is one of the things. As far as how the reduction happens, it is a two-step process. I'm not going to get into it. Here's what I want you to know. If we start out with an aldehyde, okay, and we reduce it, don't worry about this right here. Sorry, it's kind of actually hard to explain without going into the details. It's a two-step process, but what you end up with is this right here. Okay, this is, look, because of the functional group, this is an alcohol. So if we have an aldehyde, basically what happens, here's what I want you to know. I wish I could just draw this out. I'm gonna zoom in. Aldehyde. Right, this is an aldehyde. There's our H, and there's our some kind of R group. So if we reduce this, some sort of reducing agent, what happens is this becomes an O. Whoops, that goes from a double bond to a single bond. This becomes an OH. This right here stays the same. So all that's happening is the O here becomes an OH. And the double bond becomes a single bond. Okay, so if you reduce an aldehyde, you get an alcohol. Now, what kind of alcohol is this? Primary, secondary, tertiary?
Is it a secondary
So remember to,
or is it primary?
so to count it, you look at how, to determine it, you look at how many other, this is the carbon I'm trying to label. It's only bonded to one other carbon. This R group stands for some kind of alkyl carbon group. Okay. The rest of the bonds are to oxygen and hydrogen. So this produces a primary alcohol. So basically, I'm just saying, I'm not going to ask you anything about these steps on the exam. Okay. I'm not saying it's not important, but for time's sake, we really just don't have time to get into. Okay, what about a ketone? Here's our ketone right here. If we reduce it, we are going to break this double bond right here. That's going to become a single bond. And we have electrons to play with now. So we are going to, because when we break this double bond, now this carbon only, right now it has 4 bonds. When we break that double bond, now that carbon only has 3 bonds. So we have space to add on a hydrogen right here to the carbon to restore the 4 bonds to carbon. And then we add a hydrogen right here from oxygen. Now, as far as this part being from H3O plus and that being a hydride ion, don't worry about that. All I want you to know is that if we reduce a ketone, we produce an alcohol. Specifically, what kind of alcohol? If you reduce an aldehyde, you get a primary alcohol. If you reduce a ketone, what kind of alcohol does it look like we get?
Secondary.
So, well, who said it?
Bree, secondary, or Robin, sorry.
Yep, secondary. Okay, we got one bond to a carbon here, one bond to a carbon here. So that's 2 bonds total. So we get a secondary alcohol. Okay. Questions on that? This is actually really, really important biologically. So when we get to like, y'all have heard of the citric acid cycle before? Or the Krebs cycle? Y'all heard of that? You
Yeah.
haven't, it's okay. So we're gonna really get into some of those important things, and this is an example. What do we have right here? We have a ketone, right? And when we reduce it, okay, so in biological systems, there's a coenzyme. We'll look at NADH a whole lot later, but that is the common source of, notice we're putting hydrogens on these aldehydes or these ketones to reduce them. And that is the common source of the hydrogens, okay, in biological systems. So this is a really, really important part of how our body produces energy, all right? You don't have to memorize anything off this slide. I just wanted to give you a real example of how reduction of ketones right here produce secondary alcohols. Anybody heard of lactic acid before? How do we generate lactic acid when we do a workout, right? And then your muscles get really sore because of lactic acid. That's what the uncomfortable sore feelings from. So anyways, ketone to a secondary alcohol. That's just a real example. We'll look at that later. Okay, practice. Let's practice this. What product would be obtained if we reduce benzaldehyde here? So we have an aldehyde and we're going to reduce it. So basically on an exam, it might look like this. I might say we have some sort of reducing agent. Okay, or I could say H2, something like that. We're adding hydrogen somehow. We're increasing the number of carbon-hydrogen bonds. So this is an aldehyde. Well, I want you to draw the product. Anybody got it? Claire, what do you got? You nodded.
So I changed the double bond to a single bond and I
Okay,
put
so
OH.
Redraw my ring structure real quick. Let me catch up. Okay, so you drew your carbon and you said you change it to a single bond.
And I put an OH.
Okay,
And then I put another bond with or I kept the same bond with carbon and added the hydrogen.
right there, just like that. Remember what we said, let me scroll back up. We have an aldehyde. Aldehydes produce primary alcohol. So is that what we got? Do we have a primary alcohol? This carbon has only one other carbon bond. So yeah, this is a primary alcohol. So all that we're doing, oh, Cameron, what?
Would it be wrong if you added another hydrogen bond to the carbon?
No, in fact, we need one, don't we? So this is the, here, if this is our, whoops. If this is our original hydrogen, I'm gonna draw that one down here. And we actually do, so what's new is this right here, and then this hydrogen right here.
Is it okay if we like bond the oxygen to the hydrogen, or does it need to be written OH?
Say that again, Robin, sorry.
Like the OH right at the top, is it okay if we bond the hydrogen off of the oxygen, or does it need to be written like OH? Like it is.
It needs to be written like it is. That hydrogen is not bonded to the carbon. You saying it's bonded to the carbon?
No, the oxygen.
It is bonded to the oxygen. So you're saying, can I draw it like that?
Yeah.
Yeah, that's fine.
Okay.
Okay. Draw line structures for each of the following compounds and the product you would obtain from the reduction of each. Okay, so we have isopropyl methyl ketone. So this is really good practice because you're having to practice drawing these out from their names, and then we're going to reduce it. So I know I have my carbonyl carbon. On one side, I have an isopropyl group. On the other side, I have a methyl group.
It doesn't matter which side, as long as the ketone's in the middle, correct?
Correct. Does not matter which side. So I'm just going to draw the isopropyl group off here. And then I'm going to draw the methyl group off there. So that is isopropyl methyl ketone. That's the line structure. You can draw it out kind of more in the Lewis structure form if that helps you. And now we are going to reduce this. I'm going to add some kind of reducing agent, some kind of hydrogen is going to be added. And we're going to get two hydrogens. One is going to be added onto here, and one is going to be added to this carbon. Everything else will stay the same except for the double bond. So just literally redraw your compound, but with a single bond to oxygen. Then you get the isopropyl group is the same, the methyl group is the same, but what's new is we have a hydrogen bonded to the OH. This is where we get the alcohol. Now we have an alcohol, and you should have a hydrogen right there. And then double check, is this what kind of alcohol should we have? Ketones, when they're reduced, they form
A secondary alcohol?
secondary alcohol, Cameron. So this is a carbon and this is a carbon. So I got two bonds to carbon, so this is a secondary alcohol. Okay. I really would love to do more practice on this, but I'm happy to do them on my office hours later today if somebody wants to revisit these, but we definitely need to finish, and I'm trying to watch our time. So remember, P stands for para if you try to do these other groups. And that's good. Okay. Here are the hardest reactions we're going to get to today. Hemiacetyl hemiketyl formation. These are some crazy words. So this is an addition reaction. We've talked about addition reactions, okay? This is like the generalized form here is if you have A plus B makes C. So this is what we're doing in a nutshell. It's just going to seem a little more complicated because we're using real biological molecules. Okay, so it's an addition reaction. So an addition reaction between a carbonyl group of some kind. So we got some kind of aldehyde or ketone. Our molecule has a carbonyl group and an alcohol form hemiacetyls and hemiacetyls. So what we've been doing is either oxidizing one to the other or reducing. We've either been oxidizing aldehydes and ketones to we've oxidized alcohols to make aldehydes and ketones, or we can reduce aldehydes and ketones and remake alcohols. So we've been going back and forth between it. But what happens if we take an alcohol and then an aldehyde or ketone and we mush them together? Okay, we react them. We add one to the other. Well, we get something called a hemiacetyl and a hemiketyl. Okay, so if we have an aldehyde, how is this an aldehyde? Well, here is our carbonyl group. I'm just actually going to highlight it. Here's our carbonyl group right here. And you see, again, remember I showed you this very early on, the partial positive on the carbon and the partial negative on the oxygen, because that oxygen is really electronegative. So keep in mind these charges here. This is really going to help direct you with this reaction. And here is an alcohol right next door. So how is this an alcohol? Well, we have this group right here. Okay, so let's just say this is something like this. CH3OH. This would be methanol. For example, if we have methanol. The way they're drawing this right here, this R is a CH3 group, and then we have the O and the H. So they're saying I got CH3 and then O and then H, and they're just drawing it like this. And why are they drawing this little partial positive and this little partial negative in? Because just like on our carbonyl group, an oxygen and a hydrogen bond, that's a polar bond. Oxygen's very electronegative, hydrogen's not electronegative. So all the all the electrons in the bond are sucked towards oxygen. Okay, so hydrogen's got the partial positive charge, oxygen's got the partial negative charge. And what they're trying to do is to help you see when you add an alcohol and an aldehyde, here's what happens. Let me erase some of my, the partial positive, I'm going to do this in blue if I can. The partial positive of the hydrogen on the alcohol is attracted to, it sees the partial negative on the oxygen of the aldehyde. See that? So this hydrogen is just going to jump ship and go from this alcohol over, it's going to bond to the oxygen on the carbonyl group. And what does that make? What is this? This is an alcohol group. Okay, so it kind of just jumps ship. And then the partial, I'm going to do this in red now, the partial negative on the oxygen from the alcohol, it sees the partial positive on the carbonyl carbon. And literally this whole group is just going to bond to that carbon. So what we actually have, if this is another carbon right here, we have an ether group and we have an alcohol group. You'll see that? An ether group and an alcohol group, all on one molecule. So this looks pretty complex, but this is what we call a hemiacetal or a hemiacetal. People say it both ways. All right. Let me read this right here. This might help. The partial negative again from the alcohol binds to the partial positive carbon from the carbonyl group. Okay, so essentially what we're doing, if I redraw, let's just say the alcohol that I'm adding is methanol. So I have CH3 and then I have OH. You see how this is an alcohol, this methanol? Where the alcohols are broken, they're broken right here. You always break the alcohol apart. You break the oxygen hydrogen bond apart. And then this whole part of the alcohol is going to be bonded to the carbon, and this little hydrogen is what bonds to the carbonyl oxygen. So you break the alcohol apart, and then you put the hydrogen on the oxygen, and you put the rest of the alcohol molecule, you bond it to the carbonyl carbon. And that from that we get what is called a hemiacetal group. Okay. Other thing to note, other thing I want to point out is the carbonyl carbon, it becomes chiral. Do you guys remember? I forgot to go over stereochemistry. I forgot I have 2 slides from yesterday. We did not finish up. It becomes chiral. I mentioned chiral yesterday, but we really haven't gone over it a whole lot. Chiral is when you have a carbon that has 4 different groups on it, 4 different unique groups. That's a chiral carbon. And we do have 4 different unique groups. We've got an OH group, we got an oxygen carbon group, we just have a hydrogen, and then some other kind of carbon group. That's 4 unique groups. So that's what we call a chiral carbon. Okay. So if you actually want a definition for what we just formed, what a hemiacetal is, it is a compound with both. It has an alcohol-like group and it has an ether-like group. I boxed those in black. Bonded to the carbon atom that at one time it used to be an aldehyde. Okay, it used to be the carbonyl carbon of an aldehyde. It's not an aldehyde anymore because we don't have a carbon-oxygen double bond. Now we call this a hemiacetal. So the telltale sign of when you have a hemiacetal is when you have an oxygen and an ether group bonded to the same carbon. That is a hemiacetal. Okay, now the same thing can happen when you have a ketone. Undergo the same reaction when you're adding an alcohol to a ketone. You're going to break the aldehyde, or sorry, you're going to break the alcohol at with the same spot between the oxygen and the hydrogen. So again, if I have methanol over here, let's just say that's the alcohol we're going to use. I'm going to break it apart right here. I'm going to put the hydrogen. Okay, it's showing you the hydrogen is going to go to the It's attracted to the negative, partial negative charge of the oxygen from the ketone. So that this time we have a ketone. And then the whole rest of the alcohol molecule, whoops, I forgot the oxygen. The whole rest of the alcohol molecule, including the oxygen, this semi-negative charge on the oxygen is attracted to the partial positive on the carbon of carbon. And we get a brand new bond from that. It's right here, bonded directly to that carbon. And just like a hemiacetal, hemiketals or ketals, they have an alcohol-like group and they have an ether-like group bonded to the same carbon. Okay, it's just that our starting material was a ketone and not an aldehyde. Okay. So I'm going to read the definitions. What we just did is we have a compound. What we formed is a compound with both an alcohol-like group, that's right here, and it has an ether-like OR group right here, bonded to the carbon that used to be the carbonyl carbon of the ketone. And that is what we call hemiketals or hemiketals. Okay. Now, do you guys remember in the chemistry class beforehand, before you started this one, at some point in a previous chemistry class, you should have heard the word equilibrium. Anybody remember equilibrium? When you have a reaction that is reversible, remember the double arrow forwards and backwards? That is a reversible reaction. You can establish an equilibrium. So hemiacetal, hemiketal addition reactions are reversible. And they establish an equilibrium. Okay, so we can restore or regain or reform, I should say, our aldehyde or our ketone from our hemicetals and hemiketals. Now, the way this happens, I think I'm actually going to show you on the next slide. Okay, so we'll walk through that step by step, and that's probably the last thing we're going to do today. But what's really, really cool about this, and this is what's going to happen when we learn how to draw monosaccharides, is this can happen with molecules like glucose. They form hemicetals and hemiketals. But what's unique about this is starting out, glucose already has an alcohol functional group and it has an aldehyde functional group already. Okay, so here's the aldehyde functional group on glucose. We saw this on the very first slide of this. So this is the aldehyde. And this is an alcohol. And we get hemicetals or hemiketals when you add an alcohol to an aldehyde or ketone. So because you have both of these functional groups within the same molecule, it can actually wrap over on itself and just make a bond. And that's how you form these cyclic sugar. This is a monosaccharide, okay? Just the cyclic form of it. So what happens is this hydrogen goes away and you get a bond between this oxygen and it bonds directly to that carbon. And so it kind of folds over on itself and you form this bond. Now we're really going to dissect this when we get to chapter 20, but I just want you to know this can happen when you have both functional groups within the same molecule and it just forms a ring structure, okay? Don't worry about this right now. I don't want you to know what anomeric carbon is. We're going to get to that in chapter 20, okay? So straight chain hemiketals are quite unstable, but cyclic hemicetal or hemispecies, when I say species, I mean like molecules. These are exceptionally stable. Okay, that's why these sugars do this a whole lot, these monosaccharides. And then monosaccharides link up and form disaccharides and big long sugar chains, and that's how we store sugar in our body and things like that. And like I just said, this happens when you have an OH and some kind of carbonyl group and they're within the same molecule. Okay. what else do we got? We got. Okay, so I don't wanna take the time to go over this right now, hold on. Yeah, I really do need to introduce this and then we're almost done. We are gonna finish up in 10 minutes. So, we looked at forming hemicetals and hemiketals. Now we can form things that are called acetals and ketals, or acetals and some people might say ketals. These are compounds that instead of an alcohol-like group and an ether-like group, these just contain two ether-like groups on the same carbon that used to be the carbon-on-carbon. Okay. So again, we're starting with either an aldehyde or a ketone. So if your starting material is an aldehyde, you're going to form an acetyl. But if your starting material is a ketone, you're going to form a ketyl group. Okay. And what happens is you have some kind of alcohol here. And just like, so we've actually already looked at this first part. This first part is forming the hemiacetal. So first we form this hemiacetal or hemiaketal. And once we form that, we just looked at that a second ago. Once we get that, if we continue adding another alcohol, what's going to happen is we'll break this right between the oxygen and the hydrogen. We'll break that alcohol apart. And this OR group is going to replace this OH group. Okay. So this OH group right here becomes the OR group from this alcohol. And so now when we're done, we no longer have the alcohol portion. We just have two ether groups bonded to the same carbon. Okay. So these are, and then it's an identical, whoops, I meant to do, this is another ether group. So I should say we have ether groups right there and right there. And that is the acetyl or the ketyl. So it's not hemi, the word hemi means you have two different kind of groups bonded to your carbon-on-carbon, the alcohol-like group and the ether-like group. But when you have just two ether-like groups, we lose the word hemi. It's just an acetyl or a ketyl. Now, again, how do I know if it's an acetyl or a ketyl? It depends on what I started with. I started with an aldehyde, I get an acetyl. But if I started with a ketone, my final product is a ketal or ketyl. Now, you'll recognize it if you look at your product, because, so if I look at this acetyl right here, you're going to retain this particular hydrogen right here. Because remember, aldehydes always have this hydrogen branched off the carbon. You don't lose that hydrogen. So if your final product has a hydrogen bonded off that carbon, my product is an acetal. Okay, but notice with a ketone, such as acetone, I don't have any hydrogen bonded off my carbon-on-carbon. Okay, so I don't have any carbon-hydrogen bond in my final keto. Okay. So that's one way you can tell them apart. I actually think this is a typo. The substitution is not identical. Whoops, I meant to mark that out. Okay. We don't have the same kind of substitution. So sorry about that. Okay, I wanted to mention this. I didn't have space on this slide. But I really encourage you in the textbook to go review pages 487 and 488, and they'll walk you through these reactions step by step. Now, I'm not going to ask you to draw me a whole reaction for forming an acetyl or a ketyl. I might show you a reaction and say, is this formation of acetyl or ketyl? But I want you to recognize it if I show it to you, okay? I want you to know the difference between a hemiacetal and an acetyl and a hemiketal and a straight ketyl. So we're actually going to practice that right now before we finish up. Which of the following compounds are hemiacetals and which are hemiketals? Okay, so we're talking about hemi right now. So hemi, remember, this means we should have an OH group bonded to a carbon, and we should have an OR group bonded to a carbon. This is the ether group, and this is the alcohol group. Okay. And then hemiketal is if our starting material was a ketone. And again, we have alcohol and an ether light group. So look at A, for example. We've got these two carbons right here, but all I see is alcohol groups. I don't even see an ether light group on here, okay? So this is neither. Remember, to be a hemiacetal or hemiketal, you got to have an ether and an alcohol group. We don't have, neither of these carbons are bonded to R groups. Oxygen and then another carbon on the other side of the oxygen. All we have is alcohol functional group. So this one's neither. But what about B? I want you to zoom in. So to figure this out, you've got to find the carbon that is bonded to both an alcohol group and an ether group. Anybody identify a particular carbon here that has an alcohol branched off of it and an ether group? Anybody see a carbon that has both?
The carbon with the two methyl groups connected to it.
I need to turn my volume up. Say that again, Cameron. The carbon with the what?
With the two methyl groups connected to it.
The carbon with the two. Oh, are you looking at C?
Oh no, I was looking at B. I was talking about the OH and the H, the alcohol and the hydrogen bond connected to that carbon.
Yeah, right here. Right here, that carbon. Okay. So this carbon has this alcohol group. I'm going to highlight that in red. That's our alcohol group. And then in blue, this is the ether group. You see how that is COC? That's where the ether is. Now we want to know, is this a hemiacetal or a hemiketal? And here's the difference. Hemicetals, these will have that the carbon that has, trying to zoom out, the carbon that has the OH and the ether group will also have a hydrogen bonded to it. That's how you know it's a hemiacetal. All right. Now, if it's a hemiketal, the carbon that has the alcohol and the ether group will have two other carbon bonds, no hydrogen. Because the starting material was a ketone, and ketones don't have a carbon-hydrogen bond. So if I'm looking at this carbon right here, I see my alcohol group and I see my oxygen. So I need to look at the other two bonds. This one is bonded to a hydrogen and this one to a carbon. So do y'all think this is a hemiacetal or a hemiketal? Like, was my starting material an aldehyde or a ketone, basically?
Is it hemiacetal?
Yes. Okay, because of this right here, you see the hydrogen bonded off that carbon. That makes it a hemiacetal. Now for C, again, we have the alcohol group, we have the ether group, so now you need to ask yourself, on that middle carbon, what else is bonded off of it? Is it to two carbons or is it to a carbon and a hydrogen? So if we're looking close, we have the carbon is bonded to two other carbons. We don't have a carbon hydrogen bond. So this makes it a what? Hemiacetal or hemiketal?
Cetal.
Hemiketal. Okay, good. Okay, guys, this is probably the most complex stuff we've gotten into. So if your head is swimming right now, this is not on the quiz. Let me calm you down right now. I don't think I put this on the quiz. You should definitely spend some time looking at this. We're kind of more at time. All I think I really have. Don't worry about this last. Okay, so we're not going to have time to get to acetyl and keto hydrolysis. So I'm not going to have any of that on the first exam, okay? But I do want to spend another couple minutes practicing this.
What about
I have a
the
question.
stereochemistry?
Stereochemistry, that probably will be on there, okay?
So we need to go over it ourselves.
Do I look over those slides? It's just these last, oh, where was it? It's just the very, very last slides from yesterday's lecture. And
Would
we
you
got to one of them right here, where we talk about things that are chiral and achiral.
Yeah. Would you mind going over those during the when we meet for the office hours?
I will totally, here's what I'll do. I'll just make a little 10-minute video and I'll explain them and I'll post that video to Blackboard. Okay.
Awesome. Thank you.
So real quick, let's practice this. We're 10:30, but we're not meeting back after this to finish lecture. So let's spend 5 more minutes doing a little bit of practice and then we're gonna be done for the day. And I will hold an office hour at 2:30. What was that, Cameron?
I have a question. So every time you see an ether, is it hemiacetal? And every time you see a ketone, is it keto, or is that just a coincidence?
Say that so every time you see an ether.
Yes, and
Well, notice that there's an ether group in both hemiacetal and hemiketal. So that's not what differentiates them. Hemiacetal and hemiketals, they're going to have an alcohol and an ether group. What makes them different, if I'm erasing, let me just erase all this. What makes them different are what's bonded the other 2 bonds to the carbon. Not the ignore the alcohol and the ether group. That's just going to help you locate which carbon you need to focus in on. Okay, once you see the carbon that you need to focus in on, because it's the carbon bonded to the alcohol and the ether group, then look at the other 2 bonds, okay? And ask yourself, do I have a hydrogen bond and like another carbon bond, or do I have 2 carbon bonds? If the other 2 bonds, so like for here, you got this, one is to a hydrogen and then another one is to a carbon. But over here, they're both carbons. You see that? That's what differentiates the hemiacetals from the hemiketals.
Okay, thank you.
Yeah. Draw the structure, this next problem, draw the structure of the hemiacetal and the hemiketal formed from these reactions. So here is my aldehyde. Okay. This is my aldehyde functional group. And here is my alcohol. Remember, these are formed from the addition of an aldehyde and an alcohol. And we're going to break this alcohol right here. And the hydrogen is going to go one place. And this whole part of the molecule is going to go another place. Okay, so this part is going to bond to the carbon, and it's the carbonyl carbon, and it's going to bond right here to the oxygen. And then this hydrogen is going to bond to the oxygen right here off of the carbonyl carbon. So what we're going to do, just redraw your aldehyde, except for instead of a double bond, make that carbon oxygen bond a single bond. Leave the hydrogen, that's got to stay there. So this blue part that I've highlighted is the same part as right here. But now what we're going to have is a single bond to oxygen, and this hydrogen from my alcohol is now going to be bonded to the oxygen that is bonded to this is my carbonyl carbon. Okay, this right here is the, okay, so this hydrogen, I'm going to highlight it in green. This hydrogen right here, this is the hydrogen that was on my alcohol. And now it is bonded to the oxygen that was on my carbonyl carbon. And the rest of the alcohol, I'm going to highlight that in red. So this whole part is now going to be bonded to this carbon. So we're going to have an O and then a CH2, CH3. That is going to be bonded to my carbonyl carbon. And is this a hemiacetal or a hemiketal?
It's a hemiacetal.
Yes. If we're starting with an aldehyde, we get a hemiacetal. And then two, you can always double check yourself. You still have a carbon hydrogen bond there. Okay. This is a ketone. How do I know that? Because of this right here, okay? Carbon, oxygen, double bond is bonded to 2 carbons. That's a ketone. And this is an alcohol. This is methanol. We're going to break this alcohol apart right between the O and the H. And this hydrogen is going to bond to that oxygen. Okay, that's the green part. And then I'll do this other part in red. The rest of my alcohol here is going to be bonded off of this carbon, OCH3, okay? And the double bond becomes a single bond. So now let's redraw our product. Draw the ring structure. And then we make this a single bond. And we have an OH, that's the alcohol-like group, but now we also have an ether-like group bonded to the same carbon, and that's the OCH3. And because our starting material was a ketone, this is a hemiketal.
So if it like it just had the ketone right there at the start, so like can you just pretty much tell it's going to be a hemiketal?
Right, if your starting material is a ketone, automatically your product is a hemiketal.
Okay.
But if you don't know what your starting material was, like I just show you, what if I just show you this on the exam and I say, is that a hemiketal or a hemiacetal? You tell me. How do you determine which one it is? I don't even tell you what your reactants were. I just say, oh, you did a reaction and you got this product. And you're trying to figure out what this
double
is.
bonded to that oxygen.
Say that again, Robin.
Well, you can see that when it's drawn out like the circle, you can see the double bond, like how it would have been a double bond to the oxygen with the carbon.
Are you talking about on the reactant over here?
Yeah, the hemiketal that you drew. How you said that if you put that on an exam, how would you be able to tell?
How could you tell this is a hemiketal? Anybody?
Is it because there's no hydrogen bonded to the
It's exactly right, Claire. If you look at this carbon right here, ask yourself, okay, what atoms do I have bonded to my carbon? If I have a hydrogen, it's a hemiacetal. But if I don't have any hydrogens bonded to this carbon, it's a hemiketal. I see that I have another carbon. I have another carbon right there below. And then I have these bonds to, I meant to do that in blue. I have these 2 bonds to oxygen, one there and one there. I don't have any hydrogens bonded to this carbon. That's what makes it a hemiketal. Well, I mean, you have an alcohol and an ether group. That makes it a hemiketal. But how a hemiketal is different than a hemiacetal, look at my hemiacetal. I have this carbon hydrogen bond. Okay. On a hemiketal, you don't have any carbon, you don't have any hydrogens bonded to the carbon that is also bonded to the alcohol and the ether group. Sure, you got plenty of carbon hydrogen bonds over here, but you're not interested in these carbons. The one that makes it, the one that is the hemiketal or hemiacetal carbon is the carbon that's bonded to the alcohol and the ether group. Okay. So we're at time today. I will certainly stick around. There's more practice over here. I will tell you this, don't drive yourself crazy with trying to do this practice problem. That's probably a little ambitious of me to put that on here. But I think the one on the left side is certainly valid practice if you want more practice with this. And it's stuff, that next problem is exactly what we were just talking about. So it's a great one to do. So that's it for today. At 11 o'clock, it goes live, but I say give yourself an hour break. Jump on at noon or something if you have time. If you want to knock the quiz out, go for it. The answers to the quiz will show up after 1 o'clock. So when everybody finishes it and has turned the quiz in, you'll be able to see the answers and what your score was to the quiz, I believe. Or you might be able to see your quiz score right after you submit it. But as far as knowing if you got one wrong, what the correct answer should have been, that'll show up after 1 o'clock today. Do y'all know how to see right and wrong answers on a quiz? You literally go into gradebook and you click on the grade itself, or there should be a little drop down arrow right next to the grade. So you either click on your number, that is your grade for that quiz, and it should take you to the quiz and it should show you the right or wrong answers. If anybody has any trouble figuring out what the right or wrong answers for the quiz was, please email me.
The quiz is over everything we've learned this week, correct?
Yeah, it's comprehensive over everything this week because I wanted to give you kind of a practice with just a small glimpse of what the exam might be like. It's worth 10 points. It's open note, open book. You got 20 minutes to do it.
So it's over. This lecture is going to be, I'm not sure because you said it wouldn't be on it, or is it
Well,
gonna
the hemiketal part, I'll double check real quick. And if there is one, I'll probably throw another question in there. But the hemicetal, I don't remember putting anything about hemicetal and hemiketals on the quiz. Okay. That's a little more complex stuff, and I didn't want it to be that crazy yet.
I have a quick question about the quiz. Is it going to be formatted where we see one question at a time and we can't go back? Or is it
No,
like,
you'll see all 5 questions and you can go
Okay.
in whatever order you want to go. Just remember to sign the integrity form first and then start the questions.
okay, thank you.
All right, I'll see you guys 2:30 if anybody wants to join me for the office hour.
Can I ask you a quick question? Since I'm not
Yeah.
able to join the office hours because I work, could you explain a little bit better for me the tert-butyl? I had trouble finding the carbon that had the 3 because each carbon I looked at either had 2 carbons or 4 carbons. I couldn't figure out where the 3rd degree.
The tert-butyl group, absolutely.
Thank you. It was on slide 5.
Right, I remember. I'll just do it right here though. So a tert-butyl group. So butyl, you guys remember, I encourage you to go back to this table a whole lot. Okay, this is where very quickly I'm grabbing information from. Methyl, ethyl, propyl, butyl. Okay, these root words, meth, eth, prop, but, so on and so forth, tells you how many carbons are in the group that's either branched off, your substituent, whatever. So if it is meth, we know if it's meth, it's a 1 carbon. So I'm going to go down here to but because that is the root word in a tert-butyl group. And we know we've got 4 carbons. Okay. Now, right here. Here is where I introduced the tert-butyl group. Okay. This is all from day 1. Okay. We said when we're attaching a group that has 4 carbons in it, the root word there, my root alkane is a butane. But if we start pulling hydrogens off, we can get different kinds of groups. And we have isomers for butane. Okay. You could draw butane like this, all in a straight chain, or you could draw butane like this, 3 with 1 branched off. Okay. And sorry, that is 3 with 1 branched off. Okay. So straight in a row, that's a butyl group. And that's a butyl group from which we have removed a hydrogen either from the first or the last carbon. Okay, so when we attach it to another molecule, we're going to have this long straight chain. If we take a hydrogen off instead of one of these internal carbons, now we are attaching a group that looks like this. And the carbon through which we're attaching this butyl group is a secondary carbon. You'll see that? That's why it's called sec-butyl. All right. Isobutyl is if we, instead of having 4 carbons straight in a row, now we have this isomer of butane. And we are attaching, if we remove, sorry, let me go back up here. Come on, like my screen is freezing. Okay. If we rip off a hydrogen from one of the outer carbons, or from either up here, we are attaching a group that will look like this, and it's an isobutyl group. Okay. But if we specifically take a hydrogen off of the internal tertiary carbon, why is it a tertiary carbon? Because it's bonded to 3 other carbons. That is a tertiary butyl group. So we just abbreviate it as a tert-butyl group. And what we're attaching is this right here. So this is literally what we drew out in class today. Now I may have drawn the line structure. The line structure to this looks like this. And then where we're attaching it, that little red line is through this middle carbon right here. Does that help click better at all, Madison?
Yeah, I think maybe I just drew mine wrong. I think that's what I did.
Can you show me what you drew?
Yes.
Okay, so you got methyl and then you got, no, that's perfectly fine. Yeah, why do you think it's wrong?
Because I don't see where a carbon is connected to 3 other carbons. I see where a carbon's connected to 2 other or 4 other. I just can't see the third. Does that make sense?
Well, once you bond it to the group, now that carbon that is the tert-butyl carbon, yeah, now it's bonded to the carbon on your other group. So now it was a tertiary carbon, and now once you throw it on the group, now it's a quaternary carbon. But the group in and of itself, so I see what you're saying, Madison, and I see how it can be confusing. So what we have here, I'm not sharing my screen anymore. Whoops. If you guys gotta go, by all means, don't feel like you have to stick around, but if you're trying to learn as well, I get that. Okay, so yes, I agree with you, Madison, that bonded to this molecule, this is a quaternary carbon, absolutely. But when we're trying to name this, all I'm doing is I'm looking at the group that's bonded. I'm looking at the group that's bonded. Okay. So I'm saying, okay, this group, if I take this whole group and I pull it away from the molecule, what group is this? That's where we say, okay, it's a tert-butyl group. When it's bonded to the molecule, yes, because of this additional bond, now it becomes a quaternary carbon. But this group is named a tert-butyl group.
Okay, yeah, that makes more sense. Thank you. I was trying to.
Okay.
So
I see how that can be confusing. We don't call it a quaternary butyl group because the group in and of itself by itself is a tertiary carbon until we add it onto the molecule, it becomes quaternary.